Hello, welcome back to another episode of CSC 263, Database Management Systems at Adelphi University. We're continuing our discussion with the internals of database management systems and the services that the DBMS provides to us when we are programming our queries. In the previous couple of videos, we talked about things like security and transaction processing and indexing. And these are all important services provided by the DBMS. But maybe at a more fundamental level, we have to think about query processing. Because remember, the SQL language that we use is a declarative language, which basically means that we tell the DBMS what we want it to do, but we don't tell it how we want it done. And of course, at some point, that translation has to happen. So I'm going to basically type my happy little SQL query, and I'm going to tell my DBMS that I want it to pull back a number of records for me and maybe only show me some of the columns of each of those records. That is not something that the DBMS can immediately execute. That needs to be translated into some form of programmatic code. And what the DBMS does is go through a number of stages in doing that. It will use rules to translate my query into something that it believes is a more optimized version of what I'm asking it to do. And those rules come in two different formats. One of them are heuristic rules, things that we know based on experience work, give us better experience. And so we can look for these patterns and we can maybe translate one pattern that may be not very efficient into a pattern that is efficient. And we've seen an example with that before when we figured out how to do a join on tables. We could on the one hand use the Cartesian product to create the full result set and then boil that down by only including those rows that have the matching attributes. Or we could use the actual natural join operator. The result is the same, but potentially one could be a lot more efficient than the other. That is an example of one of those heuristic rules. The other one is a predictive rule, where we can actually measure how well different execution scenarios work and learn how our computer system reacts to certain solutions. And then if we have options, of course, we will choose the more efficient ones. So between the heuristic rules and those predictive rules, the ones that the DBMS can rely on to figure out how to execute the queries. In order to do that, it's going to basically take our query and it's going to decompose what we are trying to make it do. And that typically yields in some form of a representation a statement in a relational algebra, using the exact same operators that we talked about in the earlier videos. Once it's done that, in a basically fairly straightforward, maybe even a naive way, it's going to try and optimize that statement using those predictive and those heuristic rules. Once it believes, the DBMS believes that the query is now in its optimal form, it can start generating some code that can be executed in order to return our results. And then once that code has been generated, it can actually execute it so that we can have our results back. What we'll look at primarily is in these first two stages, first in decomposition. In other words, how do I translate a query into a relational algebra expression? And we already practiced that, so that should be fairly straightforward. And then we'll use one example of a heuristic optimization to illustrate the point. We're not going to go into full optimization strategies, and we're not going to talk about code generation and code execution. In this video, we'll only look at optimization using a few simple heuristics. So let's start by decomposing the query. Let's say that we have this query here on the slide. Select stud ID from grades where term greater than, and then the string 2019-09. We can type this in, but as soon as we shoot this off to our DBMS, it's going to return it to us. And the reason for that is that the DBMS will do a number of checks before it even starts analyzing the query for what it means, for the semantic load of the query. First stage is syntax. Does it make sense? Is this syntactically correct? Now, in this particular case, the query is syntactically correct. There are no obvious typos in here, no symbols it doesn't understand. Had those syntax errors been there, the DBMS would have bounced it right back to me and said, I can't figure this out, do it again. The second stage would be those semantic tests. Does the query make sense the way it's written? And in this case, that will not pass muster, because in our grades table, we didn't have a stud ID column. We had a student ID column, but the DBMS is not smart enough to do these string matches on its own. So it's going to tell me, yeah, your query is syntactically correct, but you're asking me to retrieve a column that does not exist. I can't do that at the end. I don't have to go any further than this. If I would fix that, I would run into the second problem, because I'm asking it for all terms after the fall of 2019. But the way that I encoded that is by string value. And so a comparison based on strings can be done, a lexical comparison, but in this case, actually in this case it would probably work pretty well given the way that I formatted the terms as 2019-09, and the next one would be 2020-02. That would work. But if I had typed fall 2019 and fall 2020, that would have failed. And so there's a bunch of these tests that the DBMS can do before it has to start thinking. And if those tests fail, I'll get them back as a programmer and I'll have to fix that. But let's assume that we have fixed our query and that we now have one that makes sense. For example, the one over here. We have select last name from students, which we join to grades on an inner join, which has the common element of student ID in the students table is student ID in the grades table. And we're only looking for those students who received a grade for the course ID CSC263. So first we do our syntax checking on this query, and the syntax checking makes sense. There is no syntax errors in here. The second stage is the meaning, the semantic checking, and it makes sense to compare a grade of F to a grade of F and a course ID string to another course ID string, assuming of course that that's how they're defined in your schema. So that happens as well. Now at that point we can just start building a parse tree, which basically, if we look at how this works, we'll start at the bottom with our two original tables, G and S, and we're going to join those tables G and S together using, and remember that butterfly symbol, and that was a symbol for an inner join on the common ID. So at that point we have a temporary virtual table containing all students and their grades with all of their details, which we are then going to reduce to only those courses of 263, and then further reduce that to only those courses that were given an F as a grade, and we're going to further reduce that to only display the last names of the people who received an F for that course. If we do it like this, it will work, but it's fairly inefficient in a computer's memory to do it this way, because we are only eliminating data we don't need at the last stage. Right after G and S at the bottom again, we do that natural join. We have all of the students in there and all of the grades they ever had, and that has to be represented somewhere in the computer system. And only when we've done that can we start filtering out only those courses for 263, and then only those that have an F. And then for those students that we have left in their grades, we're only interested in last name. Maybe it would have been a lot more interesting if that student ID table, the S for example, were only pulling out the student ID and their last name. And forget about everything else that could be part of the students table, so we don't have to pull that into memory and remember it. Just like the grades table, maybe we're only interested in the student ID, the grade and the course ID, and forget about everything else, and then move our way forward. So by reformatting this same query, we might end up with a more efficient format. And those things I just said, we can easily summarize into a number of these heuristic rules, these rules that the DBMS can apply now that it has this parse tree in place. So the first thing we want to do is selection and projection as early as possible. In other words, if you already know that you're not going to need data either to execute the query or display its results, get rid of it as soon as you can. At that point, you don't have to load that data into memory and manipulate all of that. Next one would be to look for Cartesian products, which are immediately followed by a selection based on their common attribute. We know that as the same operator, in effect at least, as an inner join, but the way that the Cartesian product works is by first creating all of those possible combinations and then in a second stage reducing those, where had I known that I'm looking for an inner join, I would have been able to do that in one go, and I wouldn't have to have first that huge data set which I then reduce again, so that would be more efficient. Next, the most restrictive selections should be processed first. In other words, the restrictions, whether they're selections or projections, that eliminate the largest amount of data, those are the ones we should do first. We want to get rid of all the stuff we can get rid of as early as possible. And then if we have common expressions, things that repeat multiple times, we'd like to compute those once instead of having to do the same computation multiple times. When we apply these 5 principles to that same parse tree we just saw, we get this one over here. So first we have the grades and the students table on the bottom again. That doesn't change. That's where our data is, so that's where we'll have to start. But rather than immediately joining those together, we're starting to reduce the stuff that we don't need. We're starting to select down only those grades that are an F, and we're projecting from the students only the student ID and the last name. Next in the grades table, we're going to reduce all of the course IDs that are 263. So now we're doing that reduction up front, so that once we start computing our Cartesian product, we only have a small amount of data, the join that we have to compute. And lastly, we're going to get rid of the student ID because we needed that student ID to perform the natural join, but we don't need it to display to our end user. And even though the query on the right stayed completely the same, and the results that those queries produced also didn't change, the parse tree shown here is a lot more efficient than the parse tree that we started from. And the database management system will use some of these heuristics, and maybe even more heuristics than that, and maybe also predictive analytics based on measurements, how it can optimize these queries and execute them more effectively. By doing that, we'll get our results back faster, and the database management system as a whole will be more responsive. And that has all kinds of benefits. On the one hand, it has the benefit of user-friendliness, but it also means that if I'm going to muck around with locks on my transactions, the time that data remains locked is also going to be reduced, and I'm going to have a lot less chances of problems. So an optimized query execution strategy is useful to everything and everyone. After we have now computed what these optimal strategies would be, the next thing would be to translate that into instructions to the database management system. So maybe first go open this table on file and then load these things out. All of those database internals that are completely abstracted away from us. That's called the execution strategy. And then of course lastly we have to execute that execution strategy so we obtain the results that we're looking for. That is one of the added functions of the DBMS, where we don't have to worry about all of this in our code. The DBMS will do that. This was just a quick glimpse at how a DBMS goes from your SQL query to an execution strategy, but the principle should be clear. First, we decompose the query to make sure it's syntactically correct. Then we make sure we talk in the query about things that make sense, so compare values that can be compared, ask for tables that exist, ask for columns that exists. Once that is done, we'll compute our parse tree, we'll optimize our parse tree, and then we'll execute the query. The DBMS takes care of all of that for us so that we don't have to worry about it in our computer programs.